Hello, so for today's lesson, we're going to continue our discussion of the mole, and in particular, we're going to quickly review some of our calculations, and then we're going to add on just one more conversion factor that we might find useful. Okay, so far, these are the things you should know. You should know the definition of a mole. You should know what Avogadro's number is, okay? And then we've been doing calculations with these two conversion factors. So we know we can use Avogadro's number to convert moles to molecules or molecules to moles, okay? And then we also know that we can use the molar mass, so we can look in the periodic table for the atomic mass and use that to go from moles to grams and grams to mole. And this is what we watched the Tyler DeWitt video on, and then the Mega Mole worksheet. Okay, so let's just review. Let's just review that final calculation. So here is just a little illustration that you can go from grams to moles. Whenever you're doing either grams to moles or moles to grams, you should say to yourself, I need the molar mass. So again, that's what you find on the periodic table, and the molar mass is then going to be in units of grams per mole. Okay, so if we do an example problem, all right, aluminum is often used for the structure of lightweight bicycle frames. So how many grams of aluminum are in 3 moles of aluminum? Okay, so the first thing you're going to do is say we start with 3 moles, and I need to get to grams. Moles to grams, I need the molar mass. So I can look that up in the periodic table, and I find that the molar mass is 27. So that means every mole of aluminum has 27 grams of aluminum, or 27 grams is 1 mole. Okay, so I could write that conversion factor in either of these two ways, either with grams on top or grams on the bottom. Okay, so now I go back to my problem and I say, okay, well, I'm given 3 moles aluminum. So moles is on top. So I need to cross out moles and get to grams. So then I'm going to put moles on the bottom. So moles cross out, and I wind up with grams on top. And then I'm just going to multiply 3 by 27 to get my answer of 81 grams of aluminum. Okay, so hopefully that's starting to become a little more routine. We'll do more practice problems, so don't worry. But we also realized when you did the Mega Mole worksheet that you can now do problems that use 2 conversion factors. So again, we said if we go moles to particles or particles to moles, we need Avogadro's number. If we go grams to moles or moles to grams, we need the molar mass. But what if we want to go grams to particles? Then we just use 2 conversions. We go to the mole first, and then, we convert back, so we go grams to moles using the molar mass, and then we can go moles to particles using Avogadro's number. If we go particles to moles, right, again, we can use Avogadro's number, and then once we're in moles, we use molar mass to go through grams. So everything must go through moles. So your first conversion is always going to be to convert to moles. Make sense? Okay, so here's the last piece that we need to add on, and that's what do we do when we're working with gases? Okay, so gases, it's frequently hard. You can't really measure the mass, so we would prefer to work with volumes. How much space does the gas take up? So here's where Avogadro comes in. So he came up with the idea that the equal volume of gases at the same temperature and pressure contain the same number of particles. Okay, so at any given temperature and pressure, 1 mole of any gas will take up the same volume regardless of its identity. So that's actually easier. We only have to learn 1 conversion factor here. Okay, so when we're going from volume to moles or moles to volume, okay, we're going to use the volume at what we call STP. This is standard temperature and pressure. Okay, and at standard temperature and pressure, 1 mole is 22.4 liters. Okay, so here's the conversion factor we need. 1 mole, 22.4 liters. All right, and then why is Avogadro's hypothesis important? Well, it plays a role in the kinetic theory of gases, and as I said before, it just makes some of our calculations easier because it's easier to measure volume. All right, here is the all-important mole map, okay? So here, notice moles in the center. This is what I showed you before. It's just kind of prettier. So you can go from mass to moles using the molar mass. So if you start with grams, you use this conversion factor to get to moles. And then moles to particles, we can use our Avogadro's number. If we're going this way, we start with representative particles. We use this conversion factor to get to moles. And then if we want to go to grams, we use this. Okay, so this is what we've already done. And then now we can add in our volume of gas and we can see the two conversion figures we need. So I highly recommend you either write this out on your notebook or print a copy out for yourself, especially if you've been having trouble figuring out which conversion factor to use or how to set it up. This is really helpful, especially when you're doing your practice problems, okay? All right, so let's do a couple practice. So at standard temperature and pressure, we have 50 liters of helium. How many moles do we have? Okay, so let's see how we set this up. So you start with 50 liters, okay? And we know that we're going to have 1 mole is 22.4 liters. And I put liters on the bottom because I need the liters to cross out and I need to end up with moles. All right, and you should get 2.23 moles. And if I just think to myself, I'm going, oh, well, 50 liters, 22.4 liters is 1 mole. Okay, that makes sense that I have 2.23 moles. All right, what volume does 2 moles of oxygen occupy at standard temperature and pressure? Notice here we're writing oxygen as a diatomic molecule. We're going to come back to that at the end, but for now, just know there are some gases that always occur in these doublets. So we're just going to use that, okay? So what volume? So now we're going moles to liters, okay? So we're going to start with 2 moles of oxygen. Okay, pause the video for a second and see if you can put the next conversion factor. Okay, so here's the conversion factor. So now notice we've switched it because we need moles to cross out, so that has to be on the bottom. And we're looking for volume, so the liters is on top. Okay, and if we calculate through, you should get 44.8 liters. Okay, so that's not very hard, hopefully. All right, here's a good practice problem. See if, get your mole map. Start with 50 liters of N2, all right, at standard temperature and pressure, and figure out what the mass is. Okay, so here we have N2 again. So when you're doing your molar mass, if we go back to this, notice we have 2 moles of oxygen, and we just needed to go to liters. But here, when you're figuring out your molar mass, don't forget that this is N2. Okay, pause and see if you can write it out. All right, so if you are having trouble, here's what you want to start with. 50 liters, so that's what we know we have, of N2. All right, and remember, we always go to moles first. That's in the middle. So look and see, what do you need to go from liters to moles? And then once you have moles, figure out which conversion factor you're going to go that's going to then give you grams. Okay, pause it again if you need to. All right, and here's the answer. So we started with 50 liters. Here's our mole. 1 mole is 22.4 liters. Liters is on the bottom so that we can cross that out. All right, now we have moles. So now we need our molar mass. And again, moles has to be on the bottom. So let's cross that out. And if we look for our molar mass, If we look for N2, so nitrogen is about 14. So if we have 2 of them, we're going to have a molar mass of 28. So now we're going to take 50, divide by 22.4, multiply by 28.01, and oops, I didn't put the answer there, but hopefully you can figure that out. All right, and my last little piece is I wanted to bring up these diatomic gases. So this is something you're going to have to memorize because this is going to come up more and more as we do some of these problems in the next few units. So these following 7 gases always occur as 2. So H2, N2, O2, F2. So when we're doing our reactions coming up in that unit, we always have to write these as the diatomic ones, okay? So I came up with a mnemonic. Okay, I'm not going to lie. I Googled one. I have no bright or clever friends. So that can help you. If you Google this, there's another mnemonic that I actually like better, but I didn't want to give it to you. So you can Google it yourself and see what it is. Okay, so I hope this is helpful. Your assignment now is to do the CK12 10.2. So I posted that on Google Classroom. And so it reviews some of our other problems, and then it adds in the gases. See how you do, and let me know. Have a great day.